Today we're going to talk about some basic proofs in number theory. The content that we cover is likely stuff that you've seen before at some point in life, but you've also likely never thought about why it's true or when it's true. So here's some definitions that I'm sure aren't new to you. The idea that we have prime numbers. Prime numbers are positive integers whose divisors are only one in itself. And also the idea of composite numbers. A composite number is any number that is not prime. That is, it has divisors other than one in itself. So if we list out the first 10 prime numbers, we get 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. And if we fill out the first 10 composite numbers, we notice that those are all the numbers that fill in the gaps. So 4 is not in the list of primes, so it'll be on the list of composite numbers. And say 12 is not in my list of primes, so it'll also be in my list of composite numbers. Now, when we talk about numbers being composite, this is like the idea of numbers being irrational. Like when we said, what does irrational mean? Well, it meant not rational. Composite means not prime. So ideally, what we want to have is some kind of characterization of composite numbers that's useful to us when we're looking to prove things. So this lemma is actually such a characterization. So an integer, n greater than or equal to 2, is composite if and only if there exist integers a and b such that n equals a times b, where 1 is less than a is less than n, and 1 is less than b is less than n. So a and b are not 1 or n, and we can multiply them together to get a product of n. So that's our characterization of composite numbers. Now that lemma would be used to prove this theorem that we're going to state without proof. It's really interesting, though, to think about why these things are true and think about how that lemma, our characterization of composite numbers, might be useful in proving this theorem. So the theorem is that we have a, b, and c, they're integers, and a is not equal to 0. Now, we have three things that we know. If a divides b, then a also divides b times c. The second thing we know, if a divides b and b divides c, where b is not equal to 0, then a divides c. And finally, our third item is if a divides b and a divides c, then a divides the quantity bx plus cy for every pair x and y of integers. And we'll come back to what that sum is called next class, actually. So the division algorithm is something that you learned probably in elementary school. So this is division with remainder. So if we have positive integers a and b, we can write b equals a times q plus r, where r is between 0 and a. It can be equal to 0, but not equal to a. Q is the quotient, r is the remainder. And in fact, we know that q and r are actually unique. Now, this is actually called the division algorithm. So the idea that there exist unique integers, q and r, such that b equals a times q plus r, with r greater than or equal to 0 and less than a, is the division algorithm. Now, the division algorithm is stated for positive integers, but there's really no reason that they have to be positive. They do need to be not equal to 0, or specifically a needs to be not equal to 0 in order for q to have to be unique. If a equals 0, then q is not unique. So if we have a and b with a not equal to 0, then we still have unique integers q and r such that b equals a times q plus r, and r is greater than or equal to 0, and it's less than the absolute value of a. So our a value in this case could, of course, be negative, since we're looking at integers that encompass all of the integers but 0. Now, really, this example is just giving you an idea of here are the unique Q's and R's. This is really just practicing division with remainder. So I'm not going to take the time talking through that. I'm going to hope that if you need that refresher that you take the time. Please do so.